All right. So we're going to do 1/6 notes. So just follow along and then copy down the notes as you see them. Pause whenever you feel like you need to. All right. So inverse function result from switching the x and y values. So normally when you have a domain and you plug it into a function, you end up going to a range, which is basically all your y values. So you have your domain, usually it's your x, and then you end up with your range as the y. When you use the inverse, you usually have your range, which is your y, and it takes you back to your domain, which is the original value. And that's pretty much what an inverse does. It should take you back to where you belong in terms of your domain and your original values. So one thing that you're going to have to do is verify an inverse. So if you look at the formula where it says here and here, it doesn't matter whether you have an inverse or a function. You're basically going to plug one into the other, and if you end up with x, that means that then you have an inverse. So this right here, just remember, this is inverse function notation. So if you see that, that means that it's the inverse, and the other one is just your regular function when you're using f. So in the example down here, you have a function f of x and g of x, and we just want to verify that one is an inverse of the other. So it doesn't matter which way you go. You can decide to go f of g or g of f, but as long as you end up with x, you should have your inverse. So I'm going to go f of g. So if you remember from the last section, we're going to plug in g of x into the function for f. So g of x is 5x plus 4. So we're going to take all of this and plug it in just into this x for f. So on my next line, you're going to see that. So you're going to have 5 divided by, and I'm going to put this in parentheses, 5x plus 4. And then you have minus 4 on the outside. So all I did was take the 5x plus 4 and then plug it into the x in the f of x function. So when I do that, you end up with 5, and then you get 5 over x plus 4 minus 4, which these are going to cancel out and obviously become 0. So I'm crossing those out because those are gone. And then now you're left with 5 over 5 divided by x, which when you simplify this, that x is going to jump up to the numerator. So you're going to end up with 5x over 5, and then these cancel, and you're done. That's it. We just showed algebraically verifying that f and g of x, they're inverses of each other. I could have gone the other way. You should end up with that, and maybe when we come back, we'll go over that. Moving on. So another way to verify the existence of an inverse, you're going to obviously plot values. We have the function x squared, so we're going to fill in the table. So negative 2 squared is 4. Negative 1 squared is 1. 0 squared, 1 squared, 2 squared, 4. So I'm just filling in the table. Next set of directions, interchange the rows of the table. So you're basically going to flip-flop up here and change the direction of what the table was. So this is going to be 4, 1, 0, 1, 4. This is going to be negative 2, negative 1, 0, 1, 2. So here we have our functions, we have our values. And if I notice is the second table a function, if you pause and take a moment to think, you should come up with the answer. So what it is if I circle, you have 4 and 4. So 4 goes to plus or minus 2, right? Because you have 2 possible values for 4. Is that, so this is not a function because 4 cannot be plus or minus 2 at the same time. So let me write that cleanly. Because that's two values, two different y values for the same x value, and we talked about how that means. So what does this mean in the big picture? Is not every function has an inverse. So when we go to look for inverses and solve them the informal way, we're going to find a function, but then we have to determine if that's actually an inverse function or not. So moving on to the next page. We're looking at this idea, one-to-one. To have an inverse function, a function must be one-to-one. That means that no two elements of the corresponding f function, so your f function, has the same element in the range, right? So we can't go to the same value, and that's what it means in order for us to actually verify if we have an inverse. So this is what we're doing. So just highlight the fact that this is. So graphically, what you're going to do first is check your vertical line test. So if you look at example 1 and 2, they both pass vertical line test. So I'm going to make that note, passes vertical line test. Passes vertical line test. And then the follow-up to this is, does it pass the horizontal line test? Which is similar to the vertical line test, but draw a horizontal line on both of these. And if you note for this one, if you were to move that horizontal line, which I can do, up and down, it's only going to pass at technically one place. So this one on top passes horizontal line test. So thus example 1 is 1-to-1. So it has an inverse. All right. Checking example 2. You can see that it crosses in two places. So since example 2 does not pass horizontal line test, it is not 1-to-1. Therefore, it has no inverse. And so that's going to be something where we're going to just check vertical and horizontal line tests, and if it passes both, you have an inverse. If it doesn't pass both, it could be a function, but it may not have an inverse, and that's okay. So you're going to do a couple of examples like that. Next. So here we have 3 ways to find inverses. So just kind of looking at certain problems. First one is swapping order pairs. So if you swap order pairs, we mean -8, -7, and 6 go as your x, and then -2, -1, 0. So if you look at every element in x, every x value has a different y value. Well, not a different y value. And you don't have the same x going to the same place like what we talked about earlier. So this one is an inverse. So this one's an inverse. And we're good. Now, next example. You can switch 9 and 3, 4 and -2, 1 and -1. So flipping the order of these. And if you look, once again, every x has one y. Every x, or I would say x value does not go to two different y values. So this is an inverse and how you find it. Moving on to the next part, solving algebraically. So we can call this one informally, where this is where you verify or find the inverse and just see if it's something that works. So for this, if you guys remember, if this is your function f of x and you have trying to find the inverse, we're going to switch the x and the y. So remember, don't forget f of x is the same thing as y. And then for solving for the inverse, switch x and y. And then solve for y. So that function is f of x equals 3x minus 7. So I'm going to rewrite that to solve for this as x equals 3y minus 7. So I'm going to solve for y. So I'm going to do x plus 7 by adding over the y. And then divide by 3 both sides. So I get x plus 7 divided by 3 equals y, which is the same thing as f inverse of this. So your inverse is this, x plus 7 all over 3. So those are your examples. Let's do another. So for 4x squared, I'm going to do the same thing. I'm going to switch the x and the y. So I'm going to go ahead and do that. So I'm going to do x equals 4y squared. So I am going to solve for the x. So 1 over 4 equals y squared. Take the square root of both sides. X over 4 equals y. And there is a plus or minus. And then final result, you can take the square root of 4 in the bottom, but not the x. So this is going to be plus minus square root of x divided by 4 equals y. So this one here, I'll clean it up. For this function, obviously we've kind of seen these already, but this one, first off, is it an inverse when we finish solving this? Or not an inverse? Is this a function? Well, it doesn't pass vertical line test, VLT. So because of that, this has no inverse because you do not actually have a function, so therefore we do not have an inverse. But if you were going to obviously write the inverse, that would be the function. So I'll fill in the rest. You guys can try it on your own, but on the video, I'll leave it for that for you to see how it finishes. Last thing we're going to talk about is on the back side for number 3. On a graph, reflect f of x over the line x over the diagonal line. So the diagonal line of y equals x. So that's best diagonal I can do. Hopefully that looks good. So if you see a function where you have this and you can reflect it over. So for instance, if you're trying to find the inverse of a line, any line, you can reflect it over it. But on this, you're just looking for functions that you can see kind of mimic falling over. So like usually your x squareds, x cubes, those are things that are going to be. So on a graph, you just need to verify that a function can be reflected over the diagonal line. So like this one is going to be a simple one to see. So if you were to fold that over and graph this, the inverse would probably be, sorry, I drew that in the wrong place, there. If you were to fold that paper in half and diagonal, that would be a function that has an inverse because you have a great reflection over that, and that would be an example of something that will. When we get back on class, we'll go over more of these, but that's it for now.